Hey, welcome back. So far, we've been living in this nice, clean world of single-point charges. But let's be real. When was the last time you actually saw a single-point charge just hanging out in space? The real world is made of stuff, wires, plates, solid objects. Today, we're going to bridge that gap between the textbook theory and what you actually see in engineering. We're going to figure out how to calculate the electric field from something you can actually hold in your hand.
All right, this is where we take the big leap, the one that separates basic physics from real deal engineering. So let's just jump right in and break down the problem we're trying to solve. So you know Coulomb's law, right? It's perfect for finding the field from one tiny, lonely point charge. But what about a charged copper wire? I mean, that thing has trillions upon trillions of charges. Are we really expected to calculate the field from every single one of them and then add them all up? Nah. That's not just a pain, it's literally impossible. And this really shows you the gap we're trying to cross. Over on the left, you've got that perfect, simple little theory from your textbook. But on the right, well, that's the real world we have to design things for. We're talking charged wires, metal plates inside capacitors, and all kinds of complex shapes where the charge is smeared all over the place. So, how in the world do we handle this messy reality? Well, instead of trying to count a zillion individual charges, we're going to use a much, much smarter approach. And it happens to be one of the most powerful tools in all of physics, calculus. We're about to learn how to add up an infinite number of tiny pieces to get one single clean answer. The trick here is to just change how we look at the problem. We use this model called a continuous charge distribution. So instead of thinking about every single electron, we kind of zoom out. We start treating the charge like it's a smooth, continuous fluid that's just spread all over the object. And you know what? It's a fantastic approximation. For anything bigger than a single atom, it's incredibly accurate. And here is the big idea, the main trick. We take our big, complicated object, and we mathematically slice it up into an infinite number of teeny tiny little pieces. Each piece is so small that we can actually treat it like a simple point charge. And we give this little bit of charge a special name. We call it dq. This image just lays out the whole strategy perfectly. You take your charged object, maybe this line here, and you zoom way in on one tiny little piece, dq. Now that tiny charge creates its own tiny little electric field, which we'll call dE. So what do we do next? We just use calculus. Specifically, we integrate to add up all those little dE contributions from every single dq along the entire object. It's that simple and that powerful. And look, this isn't just some abstract math puzzle. The author of our source material, Imeno Sidiku, he nails it right here. This is the absolute core skill of an engineer, taking a fundamental law of physics and actually applying it to solve a complex real-world problem. This exact method is the foundation for designing everything from antennas to high-voltage gear. Okay, so if we're going to be using this dq concept, we need a way to actually define it for different shapes. This is where we bring in our essential tools for the job, the 3 types of charge density. This table right here, this is your new best friend. Seriously, let's break it down real quick. If you have a 1D object like a thin wire, we use line charge density, or ρL. It's just charge per meter. So our tiny bit of charge, dq, is just that density, ρL, times a tiny bit of length, dl. Makes sense, right? Now for a 2D object, like a flat plate, we use surface charge density, ρs. That's charge per square meter. So dq becomes ρs times a tiny patch of area, ds. And you can probably guess the last one. For a 3D object, it's volume charge density, ρv. That's charge per cubic meter, which makes dq equal to ρv times a tiny speck of volume, dv. And all of that leads us right here to our master formula. I mean, look at it. It looks almost exactly like the equation for a single point charge, but you'll notice 2 huge changes. First, we swapped out the single charge q for our tiny piece of charge, dq. And second, we slapped that big integral sign out front. This one formula tells the whole story. Find the tiny field from each tiny piece of charge, dq, and then integrate to add them all up. That's it. Okay, enough theory. Let's get our hands dirty and put this formula to work. We're going to see how you would actually set up a classic engineering problem, finding the electric field from a charged rod of a finite length. Now for pretty much any of these problems, we're going to follow the same 4-step game plan. Step 1, you pick a smart coordinate system that makes your life easier. Step 2, you define your tiny charge element, dq, and the distance vector, r. Step 3, you use those pieces to build your integral. And finally, step 4, you actually solve it. So let's look at the setup. Here's our problem. We've got a straight line of charge just sitting on the z-axis, and we want to find the total electric field it creates at some random point P, just floating out here in space. This diagram is key to visualizing the whole thing. All right, step 1 is picking our dq. Now, since our charge is on a line, and that line is on the z-axis, we're going to use our line charge density, rho L. Our tiny little piece of length is just a little segment of the z-axis, which we'll call dz prime. So it's simple. Our dq is just rho L times dz prime. See? Easy enough. Now, just a heads up, our source material here is more focused on teaching the method than it is on grinding through every single possible integral. So while it doesn't give us the final solved answer for this specific shape, what's way more important is that we understand the setup, because that's the part that takes real physics brainpower. So, an integral, like the one we just set up, it can get messy and fast. Before a good engineer just dives into all that calculus, they always stop and ask, is there a shortcut? And in electromagnetism, believe me, the best shortcut you have is symmetry. You really have two ways you can go about this. The brute force way is to just put your head down and grind through the math, calculating every single component of the E field. But the elegant way, the smart way, is to use a symmetry argument first. You just look at the physical setup and see if the geometry itself can tell you part of the answer before you even write down the integral. So here's the bottom line. If your charged object and the point you're looking at are symmetric, you can save yourself a ton of work. Let's think about our charged rod. If our point P is directly out from the center of the rod, then for every little piece of charge, dq, on the top half that creates a field pointing down and to the side, there's a matching dq on the bottom half creating a field that points up and to the side. The up and down parts, they perfectly cancel each other out. So, without doing a single bit of calculus, that the final electric field is only going to point sideways. That's a huge shortcut. Whew, we have covered a lot of ground here, right? We went from a really simple idea all the way to a super powerful problem-solving method. So let's just recap and put together your final E-field toolkit. All right, here are the 3 things you absolutely need to remember. First, the big idea. Take any big charged object and just break it down into a bunch of infinitely small point charges, dq. Second, use the right tool for the job, the right charge density, rho L for lines, rho S for surfaces, and rho V for volumes. Use that to define your dq. And third, the pro tip, always, always, always look for symmetry. See if you can make parts of the field just disappear before you even start the math. So we've basically unlocked the ability to calculate the electric field for pretty much any shape you can imagine. And I want to leave you with a question. Think about the tech all around you. A capacitor, an LCD screen, maybe an antenna. What device's design is suddenly a little less of a mystery now that you actually know how its electric fields are built from the ground up? Give it some thought. Thanks for watching.